All right, so welcome to June. We are in the home stretch here. A couple more weeks to go and only a couple more chapters, but we just finished talking about heat and temperature and the basic ideas of how heat transfer happens. And hopefully all that was kind of making sense. I did get a request to extend the homework from Wednesday because that homework set doesn't actually show the problem numbers, which was my bad. I apologize for that, and as I transferred them to Canvas. So I think we'll just go ahead and I'll extend that probably to Friday. The other thing that we do have to decide is what to do about the exam, because on the syllabus it said the exam was today. I forgot. And nobody reminded me. Thanks, guys. I think what I want to do with that is move the exam to Friday of this week. So let's do that. Let's make it so that the exam is going to be Friday, and it will go up through the chapter that we just did on heat. No, check that. We won't include heat. It'll just be mechanics. It won't have any thermodynamics. So it'll pick up where the last test left off. So this one will have waves, simple harmonic motion, fluids, and gravity, I think. So we'll talk more about it on Wednesday. We'll kind of nail it down, and maybe during break today, I'll kind of look back and remind myself which chapters to cover on that exam. But let's plan on that exam on Friday. Okay, so we'll talk more about it on Wednesday, but just sort of get ready for that. All right, any questions on any of the homework or anything before we move into talking about gases today? All right, well, hearing none, then we're going to go ahead and talk gases. So the next step, we're going to look at how gases work, because gases are a little bit different. When we talked about things like thermal expansion and conductivity and all that, all those formulas really work quite well for solids and pretty well for liquids. But gases are their own creature, because you think about gases, we now have all these molecules with lots of space in between them. And really what we saw when we were talking about things like, say, conductivity, the way that energy moved, you think about like that metal, your metal pan that's on a stove. You start putting the flame underneath it, it starts warming that pan up, and then eventually comes into the handle. That's going on because those particles are like tight with each other, right? There's not a lot of space. And so when this one gets agitated, it starts agitating the other one. And so energy gets transferred pretty easily. And then you get that domino effect, and they all kind of get energized until now at the end of the handle, it's hot and you burn your hand, right? But something that was required was that close proximity. And this was true about other things as well, but in general, you just want to talk about heat transfer, you need to kind of have that close connection. So when we start getting into the different states, liquid, now there's a little bit more spread. Not a ton, but there's more. The bonds are still there, but they're not as tightly bound as the solids. So there's still a lot of interaction. But then when we get to gases, now we've got molecule, another molecule, and even if this one gets excited, it's going to have to end up just colliding with this guy to give it any energy. But that collision isn't going to be as likely because they're all kind of out and about. So we kind of need to treat them separately. Gases, we need to treat them separately and look at them in a slightly different way. And so that's what we're going to do today. We'll talk a little bit about what's going on with them, how the microscopic view leads to macroscopic, big picture ideas and laws and things like that. Okay, so that's where we're heading. So let me go to the board. Excuse me. Okay, so let's start talking gases. So I'm not sure everybody's level of chemistry, and I know some of you have seen some of it. So as I'm going along, if I make an assumption at any point where I say something and I go, oh, well, for example, this is not one that I would just gloss over, but I say something like, oh, okay, and then of course this is the Boltzmann constant and blah, blah, blah. If I do that kind of thing and you go, I've never heard of the Boltzmann constant, tell me, just flag me down, because I want to make sure that I don't skip over something. I don't intend to do that, but just in case I do. All right, so just make sure you catch me on anything like that if that happened.
Real quick, wasn't
Sure.
Gibbs free energy associated with gases?
Gibbs free energy?
Yeah.
I'm not sure what Gibbs free energy is.
Okay. I'll have to check up on it then.
Can you give me just a little bit of background on it?
Not off the top of my head. That's why I asked.
Okay, I'm gonna look real
I
quick.
will.
It's kind of like something that relates like spontaneity with entropy and enthalpy. Like it can be calculated using entropy and enthalpy, and then you can use it in order to find the spontaneity of a reaction without needing to know the entropy of the surroundings.
Yep, that's exactly what it is.
Okay, well then, I guess Jacob took care of you.
Yes, you did. Thank you.
No, unfortunately, I'm not sure what that is. I've actually never even heard that term, but I'll look into it, and maybe during break or something I can get a handle on what it is and relate it back. So, all right. So what we're going to want to do here is we're basically going to want to create some laws for the gases. Like how do they behave in terms of temperature and pressure and all that. So the first one, and this is kind of the biggie, is what we call the ideal gas law. So clearly it's a law that has to do with gases. But then ideal, question is, what does that mean? Well, an ideal gas, there actually isn't quite anything that's ideal. All right, but it's close. It works really well for most of the things that we're going to deal with, and it works especially well when we're not nearing the temperature for liquefaction. Okay, or the pressure, because you can actually make a gas go liquid by increasing the pressure. So as long as we're kind of far away from it being liquid or wanting to turn liquid, ideal gas law works really, really well. And this was found experimentally, but and there are a couple of different forms for this, but the one we're going to look at first is this. Okay, so it's P times V equals N times K sub B times T. So here's what all these different things are. So P is your pressure. V is volume. So on this side, we're just taking the product of pressure and volume. All right, on the other side, so this guy, big N is the number of molecules that we've got in our gas. So it's the actual count, right? You go out and you count them. 1, 2, 3, 4, 5, 6, 7, 8, 20 billion, 6 million. That's the actual number that we've got. Okay, so that's big N, which is it's actually difficult to know precisely. especially since most gases, these molecules are microscopic and we can't actually see them.
Is there a difference between number of moles and molecules?
Yep,
Okay.
there is.
Okay.
We'll talk about that in a minute. Okay, so that's N. And then this K sub B, this is what we call the Boltzmann constant. So it's named after, he was either German, maybe Austrian, but definitely a German name. So Boltzmann was a physicist who determined this value. And like it says, it is a constant. And the value of it, K sub B, is 1.38 times 10 to the minus 23. And the units on this are joules per Kelvin. All right, so this was found, just that it needed to be 1.38 times 10 to the minus 23 to make this law and other things that you'll see in the future work as well. All right, so that's the Boltzmann constant. And then T, this is your temperature. But this temperature, Kelvin, we go with Kelvin for that. Okay, so this is your ideal gas law. So consider a situation where the number of molecules is constant. So we've got whatever our amount of gas is, but it's always that number of molecules. So we're not adding any, we're not taking any away. Well, then that N is also constant, just like the Boltzmann constant. And so what we can do is actually create sort of a conservation law from this. And so if N is constant, so if we've got a constant number of molecules, then what we get is that PV over T is conserved. So any changes in pressure or volume or temperature are going to have corresponding changes in the other two that help balance it out. And this is a little bit different than a lot of the conservation laws we've seen before, because this now involves three things. It's a little bit similar to what we saw with Bernoulli. Remember Bernoulli's equation? And that involved like velocity and pressure and change in your elevation, or those three things. So this is kind of similar. So basically, if you increase the pressure, you'd have to either decrease the volume or increase the temperature. Same thing, if you increase the volume, there has to be a corresponding decrease in pressure or increase in temperature. If you increase temperature, then there has to be an increase in either pressure or volume or both. So it's a dance. It's definitely a dance, but we know that this quantity right here is going to be conserved. All right, so kind of cool, kind of nice. So let me show you an example. It's super easy to do, but let's think about what happens in a gas engine. So in a engine, in your engine, the gasoline is vaporized, basically, and so you've got this mixture of air and gas, and it's in a cylinder, but that cylinder compresses. So, you know, when they talk about like a V6 engine or whatever, they're talking about they've got 6 cylinders. But you basically have this. Inside is this gas air mixture, and there is a piston here on top. And what it does is it compresses it. Okay, so let's say that initially we've got a pressure of 1 atmosphere, that the initial temperature is 27 degrees C. Okay, so this is what it is initially. All right, so now let's compress it. So compression happens. And a lot of times when you're talking about engines, you look at what they call the compression ratio. And let's say that for this engine, we have a compression ratio of 9. So basically what this is saying, so it'd be 9-to-1, this means that it gets compressed to 1/9 its initial volume. So whatever volume we originally had, it's going to get compressed down to 1/9 of it. Okay, so here's the question. So if the compressed pressure is 21.7 atmospheres, what is its temperature? So there will be a change in temperature because we are changing the pressure, right? We've increased the pressure from 1 to 21.7, but we've also changed the volume. Whatever it was originally, it's now 1/9 what it was before. So we should expect a change in temperature. So let's see if we can find it. All right, so we're going to have the conservation of PV over T. So we're going to have P initial, V initial over T initial is going to equal P final times V final over T final. So I'm going to go ahead and solve that for T final. So we've got T final equals P final, V final, T initial over P initial, V initial. So let's start putting those numbers in. Okay, well, I gave you some initial numbers. So our P initial is 1 atmosphere. What's our T initial?
$273.15 plus 27.
Good, yeah, we need to make sure we're in Kelvin. So if we add 273 to this, that's going to give us 300 Kelvin. And yes, it's actually 300.15 or whatever, but we'll call this good. Okay, so there's our P initial, our T initial. We also need V initial, V final, and P final. So let me keep writing some stuff down here. So V initial, V final, P final. So P final, I've got that right here. We're compressing it to 21.7 atmospheres. So this guy will be 21.7. So what we're left with is V initial and V final. Well, crap, I didn't tell you. right? How much gas, what's the volume for the gas to be in that piston?
Didn't you say it was a 6 liter, like a V6?
I just said that if you have, say, a V6, it means there are 6 of them.
Okay.
But no, I didn't give it to you. But it turns out we don't need it. Because remember that compression ratio? Let's just say V initial is V initial, right? Some amount. But if we know that compression ratio is 9, that tells me that the V final is going to be 1/9 V initial. And notice that if I put that in, those V initials are going to cancel. So it turns out that this is going to work. We're now going to get our final temperature. Well, we'll take that 21.7 atmospheres. We'll multiply that by 1/9 VI. And then we're going to multiply that by the initial temperature, which was 300 Kelvin. We'll divide by P initial, so 1 atmosphere. And by V initial, which was just V initial. So you see that those VIs actually cancel. So we'll take that 300, multiply it by 21.7, and divide by 9. And so we get that that final temperature is around 723 Kelvin. Now, 723 Kelvin probably doesn't really mean much to you. So let's convert it to Celsius. If you take away the 273, this is now 450 C. Which again, probably doesn't mean a lot to you. So I'm going to go ahead and convert that to Fahrenheit. So you multiply by 9/5 and then add 32. And so this is, I think, 842. So this original temperature is just slightly more than room temp. You may remember when we were doing the linear expansion last time, that the room temp we were finding was around 26. Depending upon which one we measured, when we measured it, it was somewhere 25, 26, 27. So we started at room temperature, and by compressing it to this pressure, it ends up increasing the temperature up to 842 degrees Fahrenheit. So pretty crazy that you can increase temperature by changing pressure and volume. Okay, well, I have something I want to show you. And we'll see if this will work out. But basically, I've got a piston. Let me switch these here. And I know for this to actually work, for you to see it, I'm going to have to put down my shades, my blinds, so that's a little bit darker. But let me explain what this is. So it's just a tube. Inside, I don't know if you can see, but there's another smaller tube on the inside. Pull it out here. Well, maybe you can see if I hold it up there. Right. So there's a little smaller tube on the inside. And in that smaller tube fits this piston. Okay, so what I'm going to do is basically treat that inner tube as this piston that we're talking about. Now, what I'm going to do with it is I'm going to put a little tiny piece of paper towel. We'll see if this works. So let me just grab it from over here. So I don't know if you can see it, but it's just a little tiny piece of paper towel that I'm going to put in here so that it sits at the bottom of the piston. So So maybe you guys can see a little bit what I'm doing. So I'm just going to set it on top there. And then put it in. Okay, so I'll go ahead and screw this on, and now we've got just that little tiny piece of paper. All right, so hopefully you see it, little piece of paper's in the tube. Now, I'm gonna put my piston, or put my little plunger here. So what I'm gonna do, I'm gonna go close up this, make it a little bit darker, but then I'm gonna push down really hard on this piston. So think about what I'm doing if we think kinetic theory, you know, or we think about the theory of gas here. So I'm going to decrease the volume, right? So I'm going to compress this gas, so I'm going to decrease it, decrease that volume. I'm also going to change the pressure a little bit. I'm looking around trying to see if I can find something to make this room even darker. Hold on, I got an idea. Anyway, I'm going to keep babbling while I'm doing this. So I'm going to change the volume. I'm going to decrease it considerably, and the pressure will have a minor change. But by doing that, by changing the volume and the pressure, then I have to have a corresponding change in temperature. Well, like what we just saw when we were doing this example with the gasoline engine, we saw that that temperature increased considerably. Well, you're going to see the same thing happen here. The temperature is going to increase considerably, and hopefully what you'll be able to see is that paper towel catch fire.
I knew it.
So,
I knew that's where this
give me
was
a second
going.
here. I'm getting pretty close to getting the room nice and dark, or as dark as I'm going to be able to get it. Okay, so the last thing I'm going to do is I'm actually going to switch views for you. I'm going to close my computer so I don't get the light from the computer on it. So this image is going to go away. But then, let me do this. Okay, so are you guys hearing two of me now?
No.
I think so.
Yeah, okay. Give me 1 second. I wasn't sure if my computer mic was still catching or not. It clearly is. Okay, but we're good. So now, let me just aim this guy. So that it's on. Okay, so I think this is about as good as I'm going to be able to do. So cross your fingers. Let's see if this works. So I'm just going to compress this really, really fast. And I want you to watch the paper towel. I don't know if you can actually see the little blob of paper towel right here with my finger. But watch that. Let's see if we can make it burn.
I love it.
Okay,
Fire.
so I don't know if you guys saw that, but I definitely saw it. I had a huge old flame.
It was very visible on camera too.
All right, so pretty crazy, huh?
Yeah.
That's really cool.
Hold on, I'm all twisted up now. My earphones are all. Let me come back to reality here. Okay, so hopefully you can see me again now that by the glow of the computer screen. But you totally saw that ignite. And if you could really see, I don't know how well it comes across now because you're getting that weird glare, but you might see it's a little smoky actually in that tube. And where the paper towel was, right there, you can kind of see it's all charred and burned. So I was able to increase the temperature enough just by changing the pressure and the volume so that that paper caught fire. So that's the ideal gas law actually in action. This is a great example. And a lot of combustion engines make use of that. Certain things like diesel engines require the compression. The compression is what makes it so that the diesel engine actually ignites the diesel fuel mix. Gasoline engines, they get ignited by the spark plug. But this sort of thing is definitely used for ignitions, for actual combustion going on. So I'm just taking this apart real quick to let it air out. Okay, so give me just 1 second here. I'm gonna open up my shades again and everything so that I'm not in a cave. That way you guys can actually see something. And put the whiteboard back because the whiteboard's actually blocking part of my window. So give me just 1 second here. All right, that's a little bit better.
Where do I get one of those?
Where can you get one of those? I'm not really sure. We get these from, there's a group called Pasco Scientific, and they actually are sort of an educational science group. Like a lot of lab equipment comes from them. And this is one of the demos that they have. I've actually never tried to search for one on my own, but they are crazy cool. And I wasn't sure how that was going to translate on Zoom, but I think it actually worked out really, really well. I've never gotten that big of a flame, to be perfectly honest, whenever I've tried this before. So it was just the right combination of
Did you ever,
whatever.
you would do that in class in Tahoe, yeah?
Oh yeah, every
There's
time I
more.
teach this.
There's more oxygen in Gardnerville.
Okay, that is true. However, I doubt that that's what it is.
I mean, you're probably right.
Although maybe. I don't think that elevation difference is enough. You know, if we're only changing by about 1,200 feet or so, 1,400 feet, I don't know if that's significant enough, but I'm glad it worked out though, because that was pretty cool. Anyway, okay, so ideal gas law for sure works. We know that it's legit, and this was a really great example for you. But there are still things we could do to make it better. All right, and so what we're going to do now is look at what's called the van der Waals equation. And van der Waals equation basically starts with the ideal gas law, but makes some improvements on it. So let me go back to the whiteboard so we can see how that goes. I'll also try to get my camera back on this thing a little bit better. Okay, so we have the PV equals Nrt. Actually, before I go to van der Waals, let me show you another, or sorry, PV equals NkBT. Let me show you another form for the ideal gas law. because this is another form that you'll often see. And in fact, it's the one that I just said. I don't know if anybody caught it, but there's another form of this. It's called PV equals Nrt. Now, you'll notice that we still have P and V and T. They're still the same, pressure, volume, and temperature. But now we've got a lowercase n and a big R. Okay, so these are now different. This big R, this one is what we call the gas constant. Okay, so this is the ideal gas constant. So it's like the Boltzmann constant, but it's the ideal gas constant. And then this n is not the number of molecules, but the number of moles. So first of all, I know a lot of you have not seen these before. So moles, we use MOL for the abbreviation for moles. And what a mole is, it's kind of weird, but a mole is related to how many molecules you have, but it's off by a factor called Avogadro's number. And I'm probably misspelling that, but guess who doesn't care? He's got 2 thumbs and is sitting in front of his computer right now, which is probably most of us. Yeah. So Avogadro, I was close, it's an O. So Avogadro's number, it's this incredibly large number. It's 6.02 times 10 to the 23rd. Okay, so think about what that is. And what this is, it's the number of molecules in a mole. So you can just think of Avogadro's number as the conversion factor. If you want to go from molecules to moles, you divide by 6.02 times 10 to 23rd. If you want to go from moles to molecules, you multiply by 6.02 times 23rd, times 10 to 23rd. So this is what a mole is. Now, it's specifically defined technically. It's the number of molecules in exactly 12 grams of carbon-12. All right, why carbon-12? I couldn't tell you, other than that's probably what they were working with. But anyway, so this is Avogadro's number. So basically, how this relates, remember we had big N was the number of molecules. That's going to equal 6.02 times 10 to the 23rd times little n. So that's the relationship between little n and big N. So basically, then R is related to the Boltzmann constant, and it's off by this same amount. So R is actually equal to the Boltzmann constant times 6.02 times 10 to the 23rd. Right, because little n, we're actually dividing by Avogadro's number, so then big R needs that to be included. So this big R then, if you were to actually multiply those out, you get 8.31 not times 10 to anything. It's just 8.31. And this is, instead of joules per Kelvin, it's joules per mole Kelvin. So it's got slightly different units, but it really is kind of playing the same role. So if you ever see this form, PV equals nRT, it is equivalent to the other one. And just in my experience, we use PV equals nRT a lot more frequently because it's easier to determine the number of moles from mass. Anyway, that's my experience. For those of you that have taken a lot of chemistry, I don't know if you agree. But
Absolutely.
yeah, you use the PV equal nRT.
Mm-hmm.
A lot.
I should probably also just let you guys know when I talk about chemistry, you have to realize that this is based off of the last time I took chemistry, which was when I was in the 10th grade, which was around 1987, 8, somewhere in there. So my chemistry knowledge is really based on my physics knowledge, which means I don't apply it as a chemist would. So if you hear me say things a little bit differently, just realize that I'm not really down with the chemistry approach. So, but it's really the same thing. And Sean will agree with me. We talk about this all the time. I give him shit and basically say chemists are physicists that just ignore the physics. And he kind of chuckles at that because it's true. Like early on, you guys don't talk about physics and chemistry at all. But then when you come and you take modern physics with me or Kathy, all of a sudden you'll go, oh, that's why all that stuff in chemistry works. So chemistry is really just specialized physics. But since I didn't specialize in that physics, I don't necessarily know the detail. Anyway, but I digress. Let me come back to this. So PV equals nRT, another form. It's just now this is called the ideal gas constant. All right, now let's look at what van der Waals did to make this a little bit better. Because we can always improve things. And even though this formula works really, really well in lots of situations, the van der Waals equation is a little bit better at describing what actually happens. Okay, so here are the first things that we're going to do a little bit differently. We're going to keep that nRT and leave it how it is. But for van der Waals, we're going to change volume and pressure a little bit. So, because none of this really changes if we look at this as a series of particles. And so this is what van der Waals did. He said, all right, let's actually look at this as a series of particles. So think of it as a bunch of little BBs or marbles or, you know, whatever. Now, each of those actually takes up volume. So when you think about that container of gas, inside that are all those little molecules. And that's not space that can be used for compression, right? Like if we've got a CO2 molecule, carbon dioxide, it takes up a certain number of space, certain amount of space. And that amount of space isn't going to decrease when we start compressing them all together. It still takes up however much space that thing does. So in terms of the volume, van der Waals went, okay, well, maybe what we really need is to take away from that the volume of all of the molecules. So what we'll do is we'll subtract N times B. So remember what N is. N is the number of moles, so it's a measure of how many of these things we have. And what B is, this is the volume of 1 mole. So if we know how much volume 1 mole of the gas takes up, that's what B is. We also could have done this in terms of the number of molecules. So if instead we change that little n to a big N, but then we need to multiply it by some amount of volume per molecule, right? So depending upon what you know, you're going to do it one way or the other. Okay, so that's the first change. We're going to make the volume so that it's V minus NV. All right, but then we're also going to change the pressure. And his rationale was this. So we've got all these particles. They are going to be interacting with each other, right? There's going to be an interaction between them. That's basically the pulling or pushing of these molecules on each other. And so that's going to increase the pressure. But that increase in pressure, it's going to depend on, first of all, how many are in there, but also the volume. Because let's say we have 1 mole. So we have 6.02 times 10 to 23rd molecules. If all of that's in 1 liter versus 20 liters, in that 20 liters, they're going to be more spaced out. They're not going to really interact with each other as much. So what we really want is more of a concentration of them. Okay, so instead of just looking at the number of molecules or moles, we're going to look at it, the number relative to volume. So we're going to look at N over V basically. Okay, but the N over V is not enough. We actually need to square that. And the idea behind the squaring of it is that, think of this as affecting all of the, let's say we got a balloon. Okay, so we got a nice spherical balloon. All of that increased pressure due to the concentration has to be spread out over the entire area. And as we saw, the entire area, that's an R squared kind of deal. So we're not just going to look at N over V, we're going to look at N over V squared. So we'll put N squared over V squared. But it's going to be proportional to that. So we'll put in A here as well. Okay, so A is a constant, just like B was a constant. And A also depends on what kind of gas you have. Now, this one's not as easy. I can't just say, like this is the volume of 1 mole of gas, because this is more complicated. Okay, but each gas is going to have its own A value that then determines how that pressure changes. Okay, so it's the same idea, but it's taking into account that these gases are actual little things that take up space, that interact with each other. And this formula now works a little bit better, even for when we start getting into the weird situations of liquefaction and all that. So this one's a little bit stronger, but notice a couple things. If you don't have very many moles, this is pretty small, and so the volume is the volume. And a mole is a lot, right? Like I was saying, a mole of carbon is 12 grams of it, right? So if you had, say, a mole of carbon dioxide, I want to say that's going to be around 28 grams. And that's a lot. That's an awful lot of carbon dioxide. So we usually are dealing with pretty small number of moles. Also, if you look at this bit, if it's a pretty dilute gas, meaning there's not a lot per volume. If it's got low density, then this doesn't really affect much either. And so in a situation like when I use this thing and compressed it down, at first its density wasn't very great. And so using good old PV equals nRT would have been fine. But then when I got it compressed down, I have the same number of moles in a much smaller volume. Then this would kind of take over. So it's kind of like anything where we go simple, we use PV equals nRT till we start getting results that don't really fit very well. And then we go to, well, let's use van der Waals, and that usually makes it a little bit better. Okay, so ideal gas law made a little bit better by van der Waals.
So was there any calculus involved in van der Waal deriving this? Because I would assume when things are tiny, you would need to use calculus.
I don't believe so, because his assumption was that they were little particles that had, you know, a specific amount of volume. And calculus, you need something that's continuous. But this isn't continuous. This is, here's a particle, here's another particle, and another, and another, and another, and another, right? So it's what we call discrete. And so in that sort of situation, you don't need calculus. So
Okay.
I don't think he needed any. I think it was more just a kind of reasoning it out, thinking about what it should look like.
Okay.
All right, let's take a break. Okay, so what I want to do next is I want to talk about the kinetic energy in gases and how that's related to temperature, because we kind of hinted at earlier. In fact, I'm pretty sure I said that temperature is a measure of sort of like the internal energy and the kinetic energy of what's of the molecules inside. So let's actually get to that. Let's see why that must be. We'll kind of derive it and see how that plays out. But I did realize that I forgot to tell you one more thing, or share with you one more thing that will come in handy later. And that's a way that we actually look at graphs of pressure, volume, and temperature, because we're not used to doing that. We're not used to having graphs of 3 variables. We're really used to doing it for graphs of things with 2 variables, right? You go back to math, that's what just about every graph is, with y's and x's. But now we have p's and v's and t's. So what we will often use are what we call pressure volume graphs, PV graphs. So let me show you what they look like and how they work, and then we'll get to the kinetic energy in a gas. So let me switch real quick. Okay, so these things we call PV diagrams. It's a very creative name, of course. Okay, so PV diagrams. What we've got is basically a graph here that has pressure as one axis and volume as the other. So when we, and this is going to really come into play later when we start talking about different kinds of things that we're doing to gases, different kinds of compressions and things like that, we're basically going to follow them on this pressure and volume chart. So then the question is, where's T? Where's our temperature? Well, the temperature, if we set a temperature, come back to that PV equals nRT. If we set temperature, then pressure and volume are inversely proportional, which means their graph is going to be a hyperbola. So what we get on these are lines of same temperature. And this one, what we call these are isotherms. So let me just help you out here. Anytime you see therm, of course, that means temperature, but iso means same. So whenever you see that prefix iso, it means same. So something that's isothermic means it's the same temperature. We'll see later, we'll talk about isobaric, same temperature, or sorry, same pressure, right? So anytime you see iso, just realize that that means same. Okay, so this is an isotherm. So this would be all of the pressure volume combinations that have this temperature. So if you were to change the temperature, you would create a different hyperbola. Like, let's say here's another one. And what's really nice about these is it's easy to look at this and know which direction we're going with our temperature. The further away we get from the axis, the higher the temperatures. Okay, so when we go in this direction, we have a temperature increase. So obviously I don't have specific temperatures here, but what I do know is that this one that's kind of up top is going to have a greater temperature than the one that's more inside. Okay, so we will do a lot with PV diagrams, but when we're talking about an ideal gas, we can create isotherms, which are just hyperbolas. And we do restrict ourselves to this portion. We never have negatives anywhere because it doesn't make sense to have negative pressure or negative volume. So this is always a first quadrant picture.
What I think
Anyway.
is, oh, sorry.
No, go ahead.
What I think is interesting is in chemistries, we always did pressure and temperature as opposed to volume.
Really?
I'm curious now as to why that is.
So pressure was still your vertical and then temperature were your
Was,
horizontal?
yep, exactly.
I could see that maybe one of the reasons is that temperature is easy to actually calculate, to measure. So you could get those data points a little bit easier than trying to determine the volume.
Maybe.
I don't know if that's actually the reason why.
Yeah, I'm curious now though.
Yeah, but in physics, we're all about PV, pressure and volume. I don't know. Maybe I'll ask Sean the next time I see him. The next time I see him, it'll be forever. All right. So let's start talking though about kinetic energy and the kinetic energy of molecules. So in order to help us out, we're going to make some assumptions. And we'll talk about whether or not we think these assumptions are very good, even from the start. We'll talk about this. But let's just look at kinetic energy. Yes. Okay, so first of all, so let's assumptions. Number one is that we've got a large number of molecules that are all identical. And when I say identical, I don't mean that they're all moving at the same speed. I don't mean that they necessarily look exactly the same or whatever, but mostly it's mass. Okay, so all of them have the same mass. And we've got a bunch of them, all right? But we're going to say that we got big N as the number of them. Okay, so another assumption we're going to make is that the particles, or the molecules, sorry, act like point masses. Okay, so they behave like particles at one little point. Okay, so there's another assumption. A third one is that the size of the molecules is very small compared to their separation. So compared to the space between them. So basically, there's plenty of room around these particles. So their sizes are very small compared to the distance of things, the distances between them. Okay. Another one is that the particles are always moving. So the molecules are always moving. Okay. And they follow Newton's laws. So the laws of physics are going to apply in there. Okay. Two more assumptions. The next one is that all collisions are elastic. So all collisions that occur, whether it's particle on particle, so molecule on molecule, or molecule and side of the container, they are elastic. And the sixth one is that the walls of the container are rigid and do not move. So by rigid, I mean they don't bend or anything like that. So as the particle comes and hits the wall doesn't move, but it's still an elastic collision. Okay, so let's talk about these assumptions. So first of all, that the molecules are identical. This is okay for the most part. It doesn't apply very well to like the air we breathe, because the air we breathe has nitrogen and oxygen and carbon dioxide and water vapor and ozone and this and that and the other thing. And those are not going to be the same masses. But where this would apply really well is like if we're talking about a balloon filled with helium. Right? So we fill it with helium, all those particles are identical. Anyway, so good assumption, bad assumption, depends. Okay, number two, the molecules act like point masses. We're going to kind of put 2 and 3 together, but they act like point masses and they're very small compared to the space between them. That's probably a really good assumption. This is going to work really well, again, as long as we're not too compressed. And molecules are small. They are super, super tiny. So it's pretty decent assumption. All right, following Newton's laws, you probably look at that and go, yeah, okay, sure. But what you're going to find out when we start talking about quantum mechanics is that Newton's laws don't always work so well. So that probably feels like one that's not needed, but it kind of is. And that'll make more sense in a couple of quarters. And then the elastic collisions, that one you should probably not be okay with, because as
Not
we've
okay with
seen,
that one.
yeah, like we've seen that not always true. In fact, rarely true. In fact, never true, right? And it's all kind of how elastic, how close are we to elastic? So this one is probably the one that you're most concerned about. But I will tell you that molecules, when they interact with each other, those collisions are fairly elastic. There's not a ton of energy that's lost. And a lot of that is actually due to electromagnetic forces, because they don't actually come in physical contact. A lot of times it's they get close to each other, and then there's electromagnetic repulsion. So you're probably right to think that that's the least realistic, but we're still going to go with it. It'll make the math easier. And then rigid walls that don't move. Again, I mean, you can imagine if all we're doing is hitting the side of this container with one molecule of oxygen, let's say, yeah, you can probably figure that that wall is not going to move much, right? Like think about the wall of your house, and if all you do is throw up a wadded piece of paper and hit the wall's not going to move. And it's kind of similar in terms of scale when we talk about molecules of gases hitting sides. All right, so here are our assumptions, and this is what we're going to use to actually build our formula for kinetic energy. All right, so let's just start with one little molecule, and let's kind of follow it and see what's going on. Okay, so here's going to be the side of the container. And here's our little molecule that's cruising in. Now, it's moving in some random direction. So I'm not even going to say that it's necessarily just going in the x direction. But its velocity is going to have an x, a y, and a z component. Okay? So we're just going to go with the velocity of this thing as a vector. It's going to be given by vx, vy, vz. Okay, so it's got those three. Now, what we are going to assume is that if we were to look at all of the particles and just go on average, we should expect Vx, Vy, and Vz to all be the same, right? Because for every particle that's moving a little bit faster in the x direction, there's going to be one that's moving faster in the y direction, another faster in the z. But overall, it should pretty much balance out. Okay, so we will assume that. Now, let's think about this particle hitting the wall. So I want to think about the force that's acting on this wall. Remember the way that we find force? It's there are a bunch of different ways we can do it, but one of them is by looking at momentum over time. So impulse. So let's look at this guy. Let's think about the momentum of this one particle and how it changes when it hits the wall. So as it's coming into the wall, it's going to have an x component of velocity, call it vx, and its mass m. So its momentum is going to be mvx to the left. After it collides and bounces back, because it's an elastic collision and because the wall is rigid and doesn't move, all of that momentum gets put back into this. And so it's going to return with exactly the same momentum, which means it's going to have the exact same velocity, just pointing in the opposite direction. So the total change in momentum then is actually going to be 2m times Vx. All right, and so then again, this is going to be over some amount of time. All right, so this is particle number 1. It's going to do this much, or apply this much force onto this. Okay, but now let's think about this delta T. Okay, so really what we're looking at is average force. So we have to think about how many momentum changes do we have over a given amount of time. Well, let's say that this is a box, like a rectangular box. So we'll even make a little 3D-ness to it. So let's think about how long it's going to take until this particle comes and hits this wall again. So if it literally is just going back and forth with the speed of Vx, it hits the side, it's going to have to go down to the other side and back before it can hit this wall again. So if you think about how far that is, let's call this, say, length L. It's going to have to travel 2L. The distance it's going is V sub x. So the time is actually going to equal 2L divided by V sub x. So the amount of time between collisions is going to be 2L divided by V sub x. Well, let me put that in here. And so we get that this force then, that 2's cancel, and we're left with m times Vx squared over L. All right, so again, that's just one particle. So if I want to know what's going on completely on this side, I have to do the same thing for all of the particles and then add them up. Okay, so I'm going to write here maybe F sub I. This is the force due to the ith particle. But if I go with the total force, it's going to be the sum of the F sub I. We're going to go from 1 to n. Remember, big N is what we use for the number of particles. So notice that the only thing that's going to be dependent upon the molecule itself is its velocity. So the mass and the length of this box I can pull out. So basically, I just need to sum up the squares of their velocities. All right. Now, what we're going to do is think of this as average. Right. So let's think of it as average velocities. So if I were to take all of these and add them up and divide by how many there are, that would give us the average. So let's turn this into an average. And if I do that, I have to multiply by n. And I'm going to turn that into a Vx squared bar. So hopefully you guys are familiar with that. If you ever put a bar on top, this just means average. I imagine that you've seen that in physics up to this point or somewhere, but if you haven't, it's that.
Is that times the average of the velocity squared?
Yeah.
Okay.
Okay. So hopefully so far so good. It really is just going back to the impulse idea for force. All right. But now let's go to that on average. We should expect the x component, the y component, and the z components to all be the same. So because we've got a large number, we can go with this, that, well, this first one isn't any kind of an assumption. This is just how we do squares. The square of the velocity is actually equal to the square of the components. That's just distance formula. But what we're going to assume now is that these are all equal. Okay, so again, it's the average of these square values. And so we figured that the average x velocity and the average y velocity and the average z velocity should all be roughly the same. So that means that we can write this as 3 times the x value squared. So I'm going to replace then, remember down here we had our average x velocity squared. I'm going to replace that with just the average velocity squared. I don't want to worry about the x component. I just want to know the overall. So if I put that in there, where we sit now is that our force is equal to the number of molecules times their mass divided by the length of this box times the average velocity square, not the x component, but the average velocity square divided by 3. So that 3, when I divide it in, brings me here. Okay, so there's our force. And that's great, but I'd rather look at pressure. I want to start combining this gas law, getting back to the idea of the gas laws and all that. So let's go back to pressure. So pressure is force per area. So what I'm going to do is I'm going to take this force that's hitting on the side, and I'm going to divide by the area. So area, that was the area of the wall. L was the length of this box. So if I take area times length, this is actually volume. So I'm going to bring that volume over here so that we get pressure times volume is equal to big N times mass times this V squared over 3. All right, now let's use the ideal gas law. So we know what PV equals. I'm going to use the first form, the one with the big N. So this is going to be N times the Boltzmann constant times temperature is equal to N times M times this V squared over 3. So there go my N's. Now all of a sudden it doesn't matter how many molecules we have. Okay. Well, now what I'm going to do is I'm going to rewrite this so that it looks like kinetic energy. I want 1/2 mv squared. So I'll multiply by 3, and then I'll divide by 2. And so I get 3/2 kb times t is equal to 1/2 mv squared. And what we just found is the average kinetic energy, right? This is an average velocity for all those different particles. So there's our average kinetic energy. So we're actually done. We got where we wanted to be. I know it's hard to tell, but let me go ahead and rewrite this. So here's what we just figured out. That the average kinetic energy in a molecule of a gas, we'll call that K bar, that's equal to 3/2 times the Boltzmann constant times the temperature of the gas. So that's the average. And so if we went with the total, so here's our total kinetic energy of a gas. We need to multiply this by the number of molecules, which is just N. So 3/2 big N times Kb times 2. And of course, if you'd rather have it in the other form, in terms of the number of moles, you may remember that the N times Kb got replaced by little n times R. So a third form, or I guess the second form for the total, would be that K is equal to 3/2 little n times R times 2. So when I said before, last week when we were talking about this, and kind of hinted at temperature is a measure of energy, this is what this is saying, at least with gases, right? That if you tell me what the temperature is, I'm going to know how much energy is actually in this thing. Or if you look at the brown one, that's how much is in each molecule. So greater temperature means greater kinetic energy. And all the rest of this, this 3/2 and the Kb and all that, that's constant. And so that's why we can just say the amount of, the temperature is really a measure of how much energy is in your object, your thing. Anyway, so kind of cool how that falls out just by looking at the definitions.
Is there a way to describe potential energy of a phase change? Like, say, water going from liquid to gas? Like what the kinetic energy would be? Or
Okay.
You get
So,
what I'm saying, right?
I think, but so first of all, potential energy, let me switch views. Okay, so remember, potential energy has to be due to something else. So when we talk about potential energy, there's gravitational potential energy, there's potential energy in a spring, for example, electromagnetic, so electric potential and stuff like that. So what we need is, if we're going to talk about potential energy, there would have to be some sort of a system, right? Some sort of system that we're talking about. If we're going to talk gravity, it all washes out, because think about, in this box, the ones up here are going to have higher potential energy. The ones down here are going to have lower potential energy. But if everything's sort of evenly distributed and stuff just kind of bounces and does its thing, on average, that's all going to be as if they were all in the middle. And so there isn't really any kind of a change there. If we're going to talk about things like electric potential or electromagnetic potential or nuclear potential, that is a whole nother story. But because I think where you were kind of going was the classical, let's take potential and turn it into kinetic and vice versa. And that's not really happening here. And then the other thing that I wanted to get on is when you talked about, so let's talk about when we change state, right? When we're going from liquid to gas or vice versa or something like that. What we just developed here is for gases only. Gases only. So as soon as we go to a liquid, so let's say we've got, carbon dioxide. No, that's a bad one because that sublimates. Let's just go oxygen, right? So we got good old O2. And we cool it down so that it liquefies, we had to remove a lot of energy. And so it's not even really smart to think of it as potential energy because there isn't stored energy anymore, right? It's energy that actually got removed. But the kinetic energy of those molecules will be much lower, but we can't follow this formula because now a lot of our assumptions don't hold. Right? As soon as we go liquid, things like the distances in between them, they're not really great anymore. And we do have to worry about the interactions of the individual molecules. Like you'll notice in this one, we didn't do anything with molecule on molecule collision. Never once. But that's part of that assumption of there's tons of them, but with huge space in between. And you can also kind of reason it as, again, it washes out that anytime two of them collide, they impart into each other the other one's X component. And now, okay, well, we just swapped it. So particle A and particle B, rename them. And they're still doing the same thing. So it's definitely more complicated when we start talking about going to different states of matter. So.
Okay.
I don't know if I answered that, but I probably talked enough that you went, all right, I'm going to say, okay, so he shuts up.
No, it's cool. I like it.
No, I'm just kidding. But sometimes I feel like that. Sometimes I feel like I just keep talking until you guys all go, okay.
No, that was completely reasonable.
All right. Cool. For once, I was reasonable. I love it. All right. So feeling pretty good about that. And it is kind of interesting, but so when we do talk about temperature is energy or a measure of energy, it's a fair assumption. And while I was saying this is gases derivation, you can kind of do things similarly for solids and liquids, and it still applies for the most part, right? So, but for gases, it's absolutely a good assumption or a good way of stating it.
So that's what thermometers do basically, is this.
Well, okay, it depends on what kind of thermometer.
Okay.
So if you go classic, like the good old, mercury in the tube, which of course now they're like alcohol in the tube or whatever, those are actually using linear expansion. So you've got a little thin tube, and as that fluid warms up, it expands, right? So you get volume expansion. And there's only one way for it to go, and that's for it to go up into the rod, into the tube. And so that's why as your temperature goes up, you see that thing go higher. As the temperature goes down, it drops because it's contracting. So that kind of thermometer actually just uses volume expansion due to temperature.
Like we did in lab, basically.
Yeah,
Okay.
exactly. Except using a liquid instead of a solid.
Yeah.
But then like where that comes in, the solid increased length is with thermostats, old school thermostats, not the digital ones. right? But the older ones had what a bimetallic strip. So think of it as, right, so here's a strip where one side, I don't know if you can see, like that's kind of brown and this one's white. They probably look the same in the video. But so like this one's made out of, say, copper, and this one's made out of aluminum. And think about what we saw with the lab last week, that those different metals expanded at different rates. So imagine that this is made of two different metals. One of them gets longer. Let's say this white side gets longer. Then what's going to happen is it's going to bend. Because on a curve, the outside of a circle is going to be longer than the inside, right? We know that S equals R theta. So it'll cause it to bend. And old school thermostats used that bend to figure out what temperature it was, so that it would, all of a sudden it bends enough and, oh, let's trigger it.
I have one of those.
Yeah, the old like dial ones and all that.
Yeah,
Um,
that's awesome. That makes so much sense.
Be careful with this, because you might destroy it, and I would hate if you destroyed it. But if you pop off the top of that, right, the little rounded bell, you can actually see in it the little coiled metal. And that little metal coil is actually made of two different metals that are plated upon each other. And the temperature change causes those to bend in different ways. But then you also have like infrared thermometers. Like these are the ones that people are using now when they want the touch-free thermometer, temperature checks. Like when I go to the college to go grab anything, I always have to get my temperature checked by the dude who's sitting there to make sure that I'm, or not make sure, but to hopefully make it so that I'm not spreading COVID, right? Now those don't use anything at all like that. They actually are reading the radiation that's coming off of your forehead. So it's taking wavelengths, basically. It's reading wavelengths of radiation and then using that to determine what temperature you are, right? So, and then there are chemical thermometers. You don't really see these very much anymore, but I remember for a while, these were kind of all the rage. They were disposable, just little like flat pieces of plastic, and on the end were a whole bunch of dots. And so you like put it under your tongue, and they pull it out, and then they would look to see which dots changed color. And like those were using chemical reactions. They had, I don't know exactly what they were, because again, not a chemist. But whatever they had, those materials would react to certain temperatures and change color. Like I'm sure you've seen things that change color with temperature, like those old like mood rings or whatever, right?
Yeah.
You put them, they're black, and then as they warm up, they start turning like green and blue and yellow. So things react to temperature chemically, and that's what those thermometers did. But each of those dots was designed so that they had a very small threshold of when they would react, right? So when it comes to how thermometers work, it really depends on what kind they are. But I don't know any that use just plain old gas. There probably are some, but the ones that, were like designed for just sort of regular people usage, I don't know of any that used gas expansion, but there might be.
That's wild.
Yeah.
It's all wild. Physics is crazy.
It is. And then what's also cool is that, and I think we talked about, I think it was this group that was talking about this last week, how did they come up with the idea for this, right? How does somebody be like, oh, what we'll do? Let's create different paints that react to different temperatures. And then we can just, apply them to this plastic, and then there you go. It's a cheap thermometer, right? Like, I don't know who those people are, but those are definitely the geniuses, right? The ones that get those sparks of inspiration and come up with crazy ideas.
Definitely.
All right. Well, I think I'm going to call it a day here, guys. I know we're kind of early, but I'm just not feeling it. Plus, we're definitely good on our schedule, other than the fact that we forgot to have an exam today. So I will look at that a little bit closer and figure out exactly what I'm going to want on the exam. So look for something for an announcement to be posted tomorrow. And I'll make sure I go in there and fix that chapter 17 homework so that it actually shows what the homework set is, and give you guys a couple more days on it. So
We were supposed to have an exam today.
yeah,
Oh shit.
yeah.
Yeah, I don't think any of us were aware.
No, none of us, not even me. So don't worry about it.
That's so funny.
Yeah. So we'll just do it Friday. I figure Friday is probably better than Monday. But anyway, so we'll talk more about that next time. But other than that, I think I'm just going to say, hey, have a great couple of days, and I will see y'all on Wednesday.
Sounds